was finishing up a lecture or so on Langlands questions 6 and 7, and that entailed a little discussion of class field theory, and then the introduction of the Weil groups. I'm running out of time, and I'd like to get on to some of the bigger questions. So I'm going to put that might be one more lecture, it might even be 1.5 or so, just on questions 6 and 7. It's important because there are things that evolved into the local Langlands correspondence, but I have said verbally, some described it a little bit. So I'm going to put those aside for the time being. I mean, it's possible I might go on and lecture a little bit more. I mean, if you maybe have had quite enough of these lectures, and so it's something that, I mean, I'm thinking of the possibility myself. It's something that, because it's good for me to think of things. I really wanted to describe some of these really fundamental conjectures is too strong a word, questions that one could ask about these things. And it might be better for me to be forced with an extra week or so of lectures to think more directly about them, rather than trying to figure out questions about periods of elliptic curves, which completely befuddled me last week, even though they're not, well. But in any case, it's a possibility that either side, me or you guys, could back out of. But let me at least think about the possibility of that. Also, no. Those I could do those anytime, and maybe not. I won't even do them because there's more important things I'd like to talk about. No, like what corresponds to exponential Galois group. Were you interested in that? I know. Just, I mean, I don't know. It's pretty. Anyway. So what? I've got a couple of things to say. First of all, on Wednesday, I think that this room is not available to us. So it's the last Wednesday in the month. So the lecture on Wednesday will be from 11 to 12 in the big room in the Bayon Center, 6083. So Wednesday, Bayon Center. That would be from and also I asked Emile to, I wrote a report, actually quite a long report on the work of Robert Langlands. Took me the better part of 2 years, but it's to appear in the Abel Prize book. They have a volume every 5 years on the Abel Prize winners. But I mention it because after sitting on it for quite some time, wondering whether I'd make more corrections, I decided to put it up on my web page. And Emile says he'll put it up tomorrow. So it's on the work. So it'll be a reference like that. The work of Robert Langlands. This is to appear in the Abel Prize volume. for 2018, 2022. So that'll be on the website, my website tomorrow, I hope. Emil said he'd get to it, probably try to get to it tomorrow. And so what I want to talk about, I mean, if the first part of this series of lectures was just basically on Langlands papers, but from a general point of view, and the second part was on a linear description of the 7 questions, then this part would be part 3. I think I may have mentioned this in my lecture, or maybe even here on the future. This should be prefaced by something that I have said. An obvious first goal, even though it's a very long-term, first and long-term are sort of antithesis of each other, but an obvious first goal, or primary goal, let's say, would be to establish, I have colleagues, one of whom is a joint author with me, who think this is way over the top and it's not very practical, but I don't agree. It's to establish Langlands' principle of functoriality. With something that I think is very close to the principle of functoriality and will probably come out, drop out with a proof of functoriality by the methods of the trace formula and beyond endoscopy. So I'm going to add this with the explicit conjectural construction of the automorphic Galois group LF. This certainly depends on functoriality because we have to define the primitive representations that go into the components of this, and those are either defined as representations that are not proper functorial images, or representations, all of whose L functions don't have a pole at s equals 1 that's any bigger than the smallest thing it could possibly be. I'm not going to rewrite that again, but in both ways of characterizing this, it requires functoriality. But I believe that a proof of functoriality along the lines of using the trace formula will conversely include whatever extra little tidbits are required for the construction of LF. But I also think, and I don't know if people, my colleagues elsewhere would agree with this. If they don't agree with using it even just for the principle of functoriality, they won't agree with this. But, and Langlands' principle, he calls it the principle of reciprocity. Which is the fact, the conjecture that every, let's say, every motivic L function is an automorphic L function. And so let's say with the explicit, to go along with this, with the explicit construction of the pure motivic Galois group GF, and the map from this locally compact group LF to this reductive complex pro-algebraic group GF, And I remind myself, we remind ourselves that this is a locally compact group and we're mapping it into a complex group. And if this came out of nowhere, people would say that's a bit of a peculiar thing to do. But now it's not after the Langlands program. Langlands program is based on the representations of something like the Galois group or the VE group, the global VE group, into the complex dual group or the complex L group. It's based on maps of locally compact groups into complex groups. So this is not a, this is what we have talked about, and it's a perfectly natural thing to consider in the context of the Langlands program. And so this is the first goal, or a primary goal, obvious primary, but long term. So this is actual proofs where what I'll be talking about are conjectures or even just questions, not proofs. But so this is sort of this is the thing that we really want. But it's a long-term goal. So by extensions, and the proof of this, I guess there's opinions do sometimes vary as to how to prove Langlands functoriality. Langlands, I think, strongly believes, and I do too, that this has to be proved by methods of beyond. I'll just write BE for beyond endoscopy, as people do. So this is a formula that this is a technique proposed by Langlands, of which the primary tool, would be the stable trace formula. All right, so that's a basic first goal. Or no, I can't call it a first goal, but that's really the underlying thing that one would need. But nonetheless, I think it's very, very important conceptually, for me anyway, and maybe for others, is to think about what, if you had this, what more could you say? And there's, yes. Yes, Langlands proposed this strategy beyond endoscopy for rather a precise strategy for using the actually stable trace formula to try to prove functoriality. I'm suggesting at some risk to myself that you could use that this perhaps is the way also to prove, I mean, just beyond endoscopy, augmented by some further techniques coming from number theory, the kind extensions of the kind that Wiles and Taylor used. So augmented by that, and together with a really, really good understanding of all Shimura varieties, that is the way to prove reciprocity, namely the existence of a pure motivic Galois, I mean the explicit existence of a purely motivic Galois group together with a map from the automorphic Galois group into it. I'm saying they both should come out. The second one come out of beyond endoscopy. The second one, albeit augmented with considerably more further techniques. That was your question, yeah. But I mean, I think there are some beautiful questions and actually some beautiful possibilities that are highly conjectural, but which we can, I think, consider now. So I'm just going to list them, and then the rest of the lectures will be on the discussion of them. For now, so this is for the future. one would like to answer. Conjecturally at least, or even just conjecturally sometimes is too strong a word to even say here, but conjecturally at least. The following. Pressing questions. So A, what is the Q structure on GF? GF is, we've defined it, we've set it up as a complex pro-algebraic group, but it's really supposed to be defined over the rational numbers. What's its Q structure? This doesn't tell us at all about that. What else? B, mixed motives. What's the structure of the widely conjectured mixed motivic Galois group? We've got conjectural construction of the motivic Galois group. Mixed motives are a much bigger picture, and what do they look like? Is there an explicit construction of them? C, exponential motives. And I suppose mixed motives. That's a larger, in a completely different direction, that's a larger collection of pure and mixed motives, which seems to be very important for many things. And I will say, even though I'm no expert on these things, but what seems to be very relevant to this, and I've profited from the instruction of the thoughts of Walid, Feynman, amplitudes. I don't have too much to say about this, but it's certainly a question that is relevant to these things. And I suppose one more thing. I never have figured out. No, I guess I want this thing down, don't I? That's the most efficient thing to do. There's more to be said on periods. There's some of these things. I would say this, certainly this, and also this. They seem to almost be windows, we hope, into completely different worlds, new worlds. And there's one connected with periods. Periods. And specifically, maybe I have mentioned, without really having a good understanding of them, yes, I have mentioned, of course, periods that arise, motivic periods, that arise from the comparison of the Durand cohomology, excuse me, with Betty cohomology. Those are motivic periods, but there's a whole another big and very exciting field is automorphic periods. And there's a whole bunch of people working on that. Don't somehow, as far as I can see, don't really consider motivic periods. And there's lots of people working on motivic periods that don't seem to consider these. But I mean, a natural question is, if we're talking about reciprocity and we're trying to relate motivic things to automorphic things, the obvious question here is every motivic period an automorphic period? So if I have time, I could at least say something about what automorphic periods are and how you might try to set this up. All right. So let me start with, well, let me start with, I don't have too much to say about A. It's an important problem. But let's start. So A is the Q structure. So we have, I haven't really spelled it out, but we have, roughly speaking, described an explicit construction of the complex motivic Galois group based on automorphic representations and the principle of functoriality. So what are we talking about here? I think I tried to say something about this last week and I hadn't thought about it, hadn't reviewed it, and maybe garbled it a little bit, but the Q structure of the motivic Galois group. And so what it's based on are two fields. There's two fields. And I'm just going to write them F, and I'm not going to write Q for the rationals, just Q for an arbitrary second field. And these are fields, and they come, I think we require this at least, well, let's require them both to be a characteristic 0. But if you'll recall, the construction of the complex motivic Galois group GF depended in a way which I didn't really spell out, but on an embedding complex embedding of F into C. And these two fields have different roles. At first glance, it's not clear why there should be two fields with two separate roles when you're talking about motives and motivic Galois group. But ordinary Betty cohomology well, Betty cohomology can have any coefficients. So Betty cohomology with Q coefficients give a functor. It gives a functor. From what? Well, from smooth projective varieties over this arbitrary field F. So this is smooth projective varieties, category of smooth projective varieties over F. And so the point is, if we have embedded F into C, we can be thinking here about just the most basic things from algebraic geometry, smooth projective varieties over the complex numbers with F, a subfield of C. And so Betty cohomology maps these things into the category of vector spaces, functor from that to the category of vector spaces over Q. I'm going to leave this field just as Q for the moment. So Q vector spaces. Betty cohomology can be taken over any vector space, over a ring actually, but we'll forget about that for the moment. So that's of course been known for centuries. Grothendieck's conjectural, and I'm no expert on this, but let me just say that Grothendieck's original conjectural theory of motives says that this functor, this old-time functor, two-dimensional real manifolds, Betty cohomology, this conjectural theory of motives says that this functor factors through an intermediate category. Or in other words, it's a composition of a pair of functors, projective varieties over F and consequently over C to motives, which one could say motives over F, and then a second functor, vector spaces, well, the second functor there, vector spaces over this field Q. So that there's an intermediate functor between this functor. So it factors, I'll say through the Tannakian. I won't define all of these words, but the Tannakian, it's an abelian category. In fact, it's more than an abelian category. It's a tensor category. In fact, over vector spaces. So that's an abelian category plus other things. Category of pure motives over F. With the extra structure of what's known. I'm not these things. These two things. These two arrows here satisfy a bunch of axioms. These also conjectures, so-called standard conjectures, and most of the axioms are things that are basically things that you would expect and you would have to have. I'm not going to write them down, but with the extra structure of what's known as a fiber functor, so through the Tannakian category of this, with the extra structure of a fiber functor, what's known as a fiber functor Q, phi, how should I see? I think I'll keep the logic like this. I'll say while the extra structure of a fiber functor phi, that's the second functor there, identifies this category here, the Tannakian category of pure motives over F, that's this thing here. This extra structure of a fiber functor identifies this category with something further. It identifies mote F with a category which I'm going to just use a slightly different symbol for it. Just I'll write it as script MFQ. That is isomorphic. I think it's isomorphic, not just equivalent. I think it's actually isomorphic. I didn't check this, but with the category with the category, I'm sorry, with a category that is isomorphic. So, so this gets identified with a slightly stronger category, which in turn is isomorphic to the category this one here, which I will call rep G F Q of finite dimensional of finite dimensional representations over Q of a reductive pro-algebraic group G, F, Q. And this is what's the motivic Galois group that we're. And so it's a motivic Galois group, a pro-algebraic group over the field Q. So this is, I think, a correct description, I hope. It's more or less correct, at least, of what Grothendieck's theory of motives gives you. I haven't described that first arrow. That's a composition of several several functors, I guess, based on algebraic cycles, basically, which enlarges the category of smooth projective varieties over a given field F. It enlarges it it basically makes a bigger category by, the morphisms between projective varieties over F or over C are just algebraic morphisms from one variety to another. And what Grothendieck did was the sort of beginnings of what he did to construct motives, he enlarged this category by including more morphisms from one variety to another. And these morphisms were not just algebraic morphisms of varieties, but he added morphisms obtained by algebraic cycles. That is to say, algebraic subvarieties of a product of two. So algebraic subvarieties of the product of X and Y, two projective, smooth projective varieties. A cycle with an appropriate property sitting inside the product can be used to increase the set of morphisms between two varieties. And and for this to work out, he then introduced these conjectures, the standard conjectures, And there's a couple of other things that had to go into it, but that's basically how motives conjecturally arose. Okay, so anyway, what we want to do is, so taking, let's say, I'll just say taking Q equal to the rational numbers, we obtain a group that we have just been considering its complex points, but we obtain GF as the set of complex points of the group G. So with this notation up here, the group GFQ over Q. No, it's defined over Q. It's defined from the Betty cohomology. It's a confusing point, but think of F being embedded in C. Think of projective varieties over the complex numbers. That comes, thinking of them in those terms, comes from F. These are varieties that start off as being defined over this smaller field F. But you give yourself an embedding of F into C, you then get projective algebraic, smooth projective varieties over C. All right, now you step back and you say, oh yes, but these things have Betty cohomology, which is defined over Q. And it's that Betty cohomology over Q that gives this group, the motivic Galois group, its structure over Q. So there's two fields. Yes, that's right. That's right. Yes, that's right.
But the group should see the field
F. Is someone going to help me on this?
The group should see the field F.
Well, I'm going to say something about that in a moment. So let's leave that just for a moment. I'm saying that this group, this motivic Galois group, the thing that we've written down, what we hope is correct, but it's certainly reasonably explicit, defined in terms of automorphic representations that with a certain property, they don't come from, it's defined over pairs, groups G, and automorphic representations of G, all put together in a pretty explicit way to get a complex group. But now the question is, this group, by the theory of Grothendieck, this group has a structure over Q. And the question is, what is it? Okay, I mean, the theory of Grothendieck really does give you this structure of this group as a group over Q. We have written it down, in what we hope is a very explicit way for the group, its group of complex points. But if we go on, we want to know what it is as a group over Q. All right. What do I want to? I still don't have this quite figured out. I'd like to be able to lower that board, one of those boards, but not block out what I've just done. So I'll take this. Oh yeah, this can be used next. What is it? Well, there's a couple of remarks in this paper that's going up on this paper, suggestions that are going in my paper on the work of Langlands. Remarks in Abel. Hint at what? They hint at a nice answer, let's say, to this question. Which I'm sure with a little thought I could figure out, but I haven't really thought about it, figured it out. But they hinted a nice answer, though I don't quite know what it is. At this point. So in any case, just to say what these hints are, following standard convention, I'm going to continue to write GF as a complex group. In fact, I'll write it two ways. So I'm going to write GF both for the desired, the sought after, the desired group over Q. This is supposed to be a group over Q, which does depend on the field F, and its set of complex points. Okay, so this is the group over Q. We don't know what it is. It's a product, its complex points are a product of complex groups taken over, fibered over the pro-algebraic product of complex groups, fibered over the Tanakian group, the Tanyama group, excuse me. But let me write GF SPL split. Let me write that, whatever this product of complex reductive groups is, it has each of those complex groups has a natural Chevrolet group, split group defined over Q. So let me write GF SPL. Not just one group, it's infinitely many complex groups, but each of them is going to have a different Q structure. That's what we're looking for. But let me write SPL for the associated split group over Q. And let me write, so I'm not sure that this is entirely correct. I haven't checked whether simply taking a split group over Q with all of these complex groups, infinitely many, put together, whether that quite makes sense, but I think it does. In any case, I'll take GF QS. What I'm looking for is a Q structure of this complex group, GF. Now we know that any group over Q is obtained from a split group, and by an outer twisting, a quasi-split group, and by an inner twisting, then, an arbitrary group. So let me write GF QS for its quasi-split outer form. That's sort of an intermediate group between the natural split group attached to any complex group and the group G, GF, that is given to us by the general theory. Good. That's still time left. Okay, so we get, so just write down what I said in words. We get GF split, and we're given GF actually as a group over Q. So we're given this as an outer twist, and this is a very particular outer twist. It's the outer twist by outer automorphisms attached to automorphisms of the diagram. Of course, there's a whole infinite raft of groups like this, but that doesn't matter. So GF quasi-split, and then inner twisting is a more complicated operation, but that takes a quasi-split group to an arbitrary group. Okay, so the hints are that the first arrow is closely related to the field of definition of the families C equals CV. You have one of these families for every factor of GF, complex factor of GF. It comes from the original automorphic representation of the group. Now, I don't want to get confused between the structure of the original group G. It's by definition a quasi-split group, but its structure is not particularly closely related to the structure of this group, but it is the first arrow. This arrow is closely related to the field of definition of the families CF that index the factors LC. These are the factors of the pro-algebraic product of GF. That's all I'm going to say. These, I mean, I haven't had time to think it through carefully, but L-adic representations, if you look at the L-adic realization of this group, these are L-adic representations, and what they really are, they're people generally talk about L-adic realizations of a motive. That would be something a little more particular than this. That would be a mapping of this group GF into a vector space, into a general linear group, maybe a representation of this group GF. But really what we want to do is we want to consider L-adic representations, I mean a more fundamental realization once we've got our group GF here is the L-adic representation would be a map of it would be L-adic representations of the Galois group, or a product over L-adic, as L varies, of L-adic realizations of the Galois group, not into a general linear group, but into this group. That's where these things lie. These things lie in this group. And when one looks at L-adic representations, as complex representations, L-adic representations of ordinary Galois groups or infinite Galois groups, you have to take a field extension. The L-adic presupposes that you're using L as a prime to index the factors of these representations. But really, what's going on is that there is a field extension. People call them lambda-adic representations. Lambda is a prime in a larger field, not Q, but a larger field. And so these things, in any case, should be maps, lambda-adic maps of the Galois group into this thing. That's a more fundamental thing, fundamental realization of this, and the realization, the motivic realization of an L-adic representation, motivic representation, would just be a homomorphism from this group into a general linear group with all of these L-adic representations already sitting in here, or sitting in each of the little factors there. And each of these L-adic representations in here, that is to say, corresponding to the different groups GC, each of them is attached to a field. And so these numbers, these are the things that reciprocity attaches to the L-adic representation. So these things should have themselves, they're not just as ordinary complex numbers, but they should have, for motivic C, they should have, they should be defined over an extension, an L-adic or a lambda-adic extension of the rational numbers. So I'll say no more about that, but I'll just say that the first arrow is closely related to the field of definition of these families that index the factors here, and also what would we say? While the second arrow, so we have to determine these two operations on this split group. This is already given to us. This one getting it into a quasi-split group, and this one getting it into the Q group that we really want. So while the second arrow up here, is related to the embedding. F into C, on which the Q structure depends. It's a rather vague statement, but it's suggestive to observe that everything that we have set up here, including the proposed Q structure of this group, depends on this embedding of the field F into C. And if you choose a different embedding, I mean, one really does want to consider projective varieties not just over the rationals. One really wants to consider them over, let's say, arbitrary, maybe number fields, F. Certainly you want to consider them over number field F. So then it's really relevant how you embed this number field into the complex numbers. Where did I write that down? It's really relevant to what you're talking about. That's not canonical. I'm looking for a canonical Q structure on my group GF. I have what I have is the set of complex points depending on an embedding of f into c. A different embedding of f into c, it's not hard to show that it gives a different inner twist. Two different embeddings of f into c are related to each other by an inner twist. So the Q structure depends, the second arrow is related to the fixed embedding on which the Q structure depends. I don't think that's a very clear statement, but the Q structure should be independent of the map from F into C. Anyway, these points are more or less just repeating what I've said here. These things are in this reference at page 129 to 130. But I think that I don't think that the description of the Q structure on the motivic Galois group is going to really be terribly difficult to figure out. It's just a question of perhaps putting these things together. Pardon me? Yes, Emil said he would post it tomorrow. Yes. All right. Oh, I went over. Sorry. So we'll on Wednesday. I mean, do you want me to continue with this on Wednesday, or do you want me to do they groups? I mean, it's not going to record as well in the other room. Shall I just go on with this on Wednesday? I should.